Our final is at 10 on Tuesday. Oh, that's a strange time, but 10 o'clock rather than 11 on Tuesday in here. Bless you. All right. Well, let's finish up section 5, which was talking about distributions associated with normal distributions. And then we'll talk about section 6, which actually turns into more normal distribution stuff when we talk about the central limit theorem. So, pardon me, goodness. Let's say we've got this problem here. They give you compact cars and mid-sized cars and means for each, standard deviations for each. And then they ask about how the means are distributed, how the difference of the means is distributed, and then calculate the probability here. So, remembering what we talked about last time. Oh, thanks. If x is distributed normally, how is x bar distributed? If x is a normal distribution, then the mean of x is also normal, right? The mean of x and the mean of x bar is what? Well, what's the relationship between the mean of x and the mean of x bar? They're the same, right? What's the relationship between the variance of x and the variance of x bar? How do you find the variance of x bar relative to the variance of x? Divide by n. Good. So in both of these cases, x bar is normal. The mean will be the same, but the variance will be the variance of the original. Notice I gave you the standard deviation, so you need to square, divided by the sample size, which in this case is 8. Y bar is also normal. The mean stays the same. Pardon me, goodness gracious. And then the variance will be 2.7 squared over 8. So that'll be your part A in that case. Basically, what the way we're doing the distribution again, just to remind, when you're doing the distribution of x bar, you're basically taking random samples of size n, in this case it's random samples of size 8. Do that over and 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 over again, you get a distribution. That distribution has a mean that's the same as the original distribution, but the variance is smaller. All right. So that's the idea here. All right. So that's part A. We good with part A? All right. I was assuming normal. Yep, sorry. Yep, we're assuming that it's normal. My apologies. This one was just asking for the means and the variances. I was assuming they're normal. You're right. The means and the variances are still the same. That doesn't change. The mean of the mean of the sample means is the same as the mean of the original. The variance of the sample means is still the variance divided by the number of not the size of your sample. The fact that it would be normal is it's also normal. All right. Sorry about that. I guess I did skip a step with the normal distribution part. Anyway, now that we have two normal distributions, which is what part B says, assuming they're normally distributed. When you have a normal distribution, if you do a sum of normals or a difference of normals or any linear combination of normals, what do you end up with? A normal, right? So what do you do with the means when you have a difference? What are you going to do with the means? Subtract them? What will you do with the variances? You got to add them, right? Remember, you always square the coefficient in front. It'd be like a -1 in front of that one, right? It'd be like a -1 there. And you always square it, right? So it's always going to, you're never ever going to subtract variances. They always get added. Even if it's a minus sign, remember the coefficients in front get squared, right? We talked about that before. If you've got variance of ax plus by, you do a squared variance of x plus b squared variance of y, right? And then, of course, you also have the extra covariance part if they're not independent, right? So it's always going to be always add the variances. You might subtract the covariance, but always add the variances. It's never subtracting the variances. That would be bad if you ever subtracted the variances because you might get a negative number. And can variances be negative? No. All right. The whole point of that problem, the whole point of part B is that linear combinations of normal distributions are still normal. That's the whole idea. Finally, on this last one, if you want the probability that x is greater than y, what would you do? Yep, subtract the y to the other side. You wrote too many vector symbols in linear, and I tried to write a vector symbol there. It's hard for me to keep track of what class I'm in, too. All right, subtract it. And now we've got basically a normal distribution problem, right? Because we already said that x bar minus y bar is normal, right? So I would do 1 minus to set it up like it's a CDF, right? I would take the 0 and subtract off the mean of the difference of the two, right? Well, we did that up here. What is that, 3.2? I just subtracted these two from each other. And then divide by, no, I'll do the square root of whatever that number turns out to be. I have to do the square root, right? Because I have that variance written there. Questions on that one? Is that okay? Yeah. So this is just this problem is just all about changing it to a normal distribution, which is we've got a lot of times, right? Okay. All right. So the next couple of problems refer to a new-ish type of distribution. I'll say new if you haven't seen it before. But this distribution pops up when you've got hypothesis testing that you want to do with small sample sizes. Okay? I know we haven't talked about hypothesis testing at all, but this is the reason why we talk about this particular type of distribution. So sometimes you get large samples, and what we're going to see when we talk about central limit theorem is that when you have large samples, things basically become normal. Okay? So we can always use the normal distribution. However, when you've got smaller samples, things may not be close to being normal quite yet. However, if the underlying distribution is normal, there's another type of distribution that you can use to help make inferences about a population. That's where all of this stuff is leading to, by the way. It's all trying to get us to statistics. Okay? All right. Pardon me. So why might you want to do something with small sample size inference versus large sample size? Well, it could be that you need to do testing on expensive things. Do you want to do a sample size of 1,000 if something costs you $1 million to make? No, right? Like, how do they test car safety? What do they do with the cars? They go out and they crash them. Do you want to crash 1,000 cars? Probably not. It's really expensive, right? You'd probably want to do the testing by crashing 10 cars or 15 cars and see what's going on. Okay. So that's why it's important to be able to have these ideas of what's going on with a small sample size. So the idea behind this is that if, make sure I write this all down like they have it in the book for you. But if you've got a standard normal distribution, so if your z is standard normal, so mean 0, standard deviation of 1, and you've got W, I'll call W is a chi-squared distribution with r degrees of freedom, then we have this distribution referred to as T, which will be z divided by the square root of W over R, is what's called a T distribution with r degrees of freedom. I do need my z and my w to be independent in this. We talked about this very, very briefly. It's beyond the scope of what we're going to do. But if you do random samples, then the sample mean and the sample variance are independent of each other. If you do random samples. This is why this is important, by the way. So if I'm doing random samples, typically we're doing random samples and making means, right? Pardon me. If the underlying distribution is standard normal, then really what I have here is a mean on top that I'm interested in, that I've standardized. And then on bottom, I've got the square root of a chi-squared over the degrees of freedom. Now remember last time we said we had that n minus 1 s squared over sigma squared is chi-squared of n minus 1. We talked about that last time, right? You agree with that? Okay. So really what we're doing down here is if I have if this thing is my chi-squared, I'm dividing out by its degrees of freedom. If I've got a standard normal distribution, this thing is 1. So really all I have on bottom is just the square root of the sample variance there, right? Okay. And so that's where this is coming from here. We're taking the chi-squared, we're dividing out by its degrees of freedom. This is what's referred to as a T distribution. But notice the format. Standard normal on top, square root of a chi-squared divided by its degrees of freedom on bottom. Okay? So what it wants you to do in this problem is look at the format of this thing and pardon me, convert it to this form. All right, so we've got x1 plus x4. What type of distributions are x1 and x4? They're normal, right? So the sum of normals is normal. What do you do with the means? Is it add them, right? Yeah, it'll be the mean. It'll be the same if you take the mean of them, but in this case we add them, but they're both 0, so it is the same in this case, right? What do you do with the variances? Add them, right? So our variance in this case will be 2, correct? Agree? Is that standard normal? No. So if I look at this fraction, just the top for right now, what do you need to put on bottom to make that a standard normal? Be a little bit careful. What goes on the bottom? What do you make it a standard normal? Not the variance, but the... What do you divide by when you do your z-score? Standard deviation. I got to put square root of 2 on bottom, right? To keep everything equal, I better put a square root of 2 out in front, right? We agree? Okay. All right, so all I did here was just convert my top to a normal. Okay? Standard normal. Converted my top to standard normal. I know it already is normal because sum of normals is normal, right? I divided by the standard deviation to make it standard normal, but of course I'm trying to keep everything equal, so I need to make sure I do root 2 over root 2 there. Okay. All right, let's look at the denominator now. What kind of distribution are x2 and x3? They are standard normal. What do you get when you square a standard normal? Chi-squared on how many degrees of freedom? I have a single standard normal and I square it, I get a chi-squared of 1. Yep, it's chi-squared of 1, right? So if I add another one, that's also going to be chi-squared of 1. And when you add independent chi-squareds, what do we get? It's a chi-squared. What do you do with the degrees of freedom? Add them. So this will be chi-squared of 2, right? Okay. So looking at what we need here, I've got a chi-squared, under my radical currently, I've got a chi-squared on 2 degrees of freedom. To make it look like a t distribution, what needs to go in the denominator? Just as I have to take the chi-squared distribution and divide it by its degrees of freedom, right? So on the bottom, I've got to put an over 2, but really that 2 is under the radical, right? So to keep everything equal, what needs to be multiplied out in front? Yes. Because I have to have the degrees of freedom in the denominator under my radical. And we just said there's 2 degrees of freedom. So the degrees of freedom have to be in the denominator. What needs to go out in front to keep everything equal? Square root of 2. And notice that the 2 root 2's on top and bottom will cancel each other out, won't they? So do I need to put any constant here in front to make this a t distribution? No. So it's one of these 2 answers, right? Because we don't need a constant other than 1 out in front. How many degrees of freedom does that t distribution now have? 2, because that's the denominator. Yep, so it must be b. This is just a little bit of practice with the distribution. Okay. I think the next one's just like this one. Let's go look at it. There it is. I should have put this one first. Is that the last one? Nope, there's one more. Should have put this one first. This is all the same idea. The top is standard normal, right? Inside the radical, we've squared a standard normal, so that becomes chi-squared of 1, and so is that one. When we add chi-squareds, we get a chi-squared with 2 degrees of freedom, and we've divided by degrees of freedom. So this is a t distribution. And usually put the number of degrees of freedom in the parentheses here. So it would be T2. What might be the most interesting part about the t distribution? It's called the student's t distribution, because the person who came up with this distribution published it under the pseudonym of student. Now you might ask, why did they publish it under a pseudonym? Well, the person was a beer manufacturer. They were a beer manufacturer. They came up with a distribution to be testing their beer. They didn't think they'd be taken seriously if it was a beer manufacturer submitting this to for publication. So they published it under a pseudonym. But this distribution came from beer. It's kind of fun. Kind of a fun little tidbit. At least I think it's a fun little tidbit. All right, let's look at the last one. But that's why it's called the student's t distribution. It was published under the pseudonym of student. Yes. We talked about that before, that when you do sums of independent chi-squareds, you get a chi-squared. Why is when I do a standard normal chi-squared of 1? That's because of you have to go back to I can't remember what that section number it is. I'm not gonna go take the time to go back through it again, but it's on page. I'll tell you what page it is in the book as soon as I find it. Normal distribution. It's on page 116 of your book in section 3.3. Yeah. They go through the CDF of it and then show that you have the same PDF as a chi-squared of 1. That's where it comes from. All right. Let's do this last one, and then I've got one more handout for you when we talk about central limit theorem. All right, so same idea here. Let's look at the top. Start with the top. X1 is standard normal, and so is X2. When I do X1 plus 2X2, what kind of distribution does it have? Normal. What will the mean be? 0 again, right? Because it's 0 plus 2 times 0, right? But what will the variance be? Careful. It'd be 5, right? We got to square the 2, right? It's the variance of x plus the variance of 2x. But I have to pull that 2 out and get squared that 2, right? So we have 4. Okay. So it's normal 0, 5. So if I look at my numerator again, to convert that to a standard normal, what do you need to divide by? Square root of 5. Good. And so we would also need to multiply by square root of 5, right? Keep everything equal. The bottom looks a little tricky. It says absolute value. Now, absolute value of x3 is the same thing as the square root of x3 squared. They're just being a little bit trickier there. Right? Remember when you do the square root of a square, you don't just get the inside, you get the absolute value of the inside. Because the squaring kills any negative that might have been in there. Okay. X3 is standard normal, right? So x3 squared is chi-squared of 1. So do we need to divide anything in this case? No, we're good. So this is still just absolute value of x3. So this is now t of how many degrees of freedom? Just 1? Good. And what's the a that we need? Root 5, yeah. So the a is, so your a is root 5. And your r is just 1 degree of freedom. It's just playing around with recognizing what you need for a t distribution. The t distribution definitely is more important when you start talking about hypothesis testing on small sample sizes. So if you're going to do any more statistics in the future, whether it's the 314 class that follows this one, or if you take 230, or any other statistics class you take, you'll probably see the t distribution in it. And you've seen statistics, you've already seen the t distribution. Well, all right, last thing we're going to talk about is what's referred to as the central limit theorem. The central limit theorem basically says is the world is normal. As long as your sample size is big enough. Did I not put this in there? Oh, I did. Okay, good. All right, so let's look at what this problem's asking us, and then I'll write down the theorem. We're not going to prove the theorem because we don't, have the time or the machinery. Where did it go? It shrunk on me. That was weird. Not sure why it shrunk on me. All right, there we go. We don't have the time or the machinery right now to prove the central limit theorem. But let's see what might be involved here. So this one tells us that we have a distribution, gives us the PDF of the distribution on the interval from -1 to 1, and then says define y to be the sum of a random sample of size 15 taken from that distribution. Well, if we were going to do this the old way, we would need to figure out what the PDF is for y and then integrate. Right? Well, notice that y is a transformation of 15 random variables. That seems like a hard thing to find the PDF of, right? We even skipped the transformations of 2 variables, didn't we? Right? We did transformation of 1 variable, right? Y was a function of x. But when we got to, say, x1 or x2 and x3, we did special cases. We did max, we did min, we've done sums of geometric, sums of exponentials, right? But that's not any of those. So actually finding the PDF here would be a difficult proposition. Now the authors of the book did, obviously, it says using the PDF they found, this is the probability. We're going to estimate it instead. All right. So how does the central limit theorem go? So this is the statement of your central limit theorem. And in your book, it is on page 207. All right. So the central limit theorem says pardon me. So if you have a random sample of size n, x2 out to xn. Oh my goodness. If you have a random sample of x1 out to xn, then the distribution of, here's what we're going to do. We're going to take the distribution of the sum of the random variables oops. Yeah, that's right. This is approximately normal with mean being n times the mean and the variance being n times the variance as in, well, I should say it goes to this, but it's approximately normal. If your n is large enough, it's approximately normal. I'm just going to write it that way. If you keep taking random samples from the same distribution and adding the results, then the sum turns out to be approximately normal as long as your n is large enough. You can discuss a different day what large enough means. Typically, when you're doing random samples, you want your n to be at least 30. That is usually enough to make it guaranteed to be close to being normal, roughly. If your underlying distribution is already normal, then you know you don't have to worry about it. It already is normal. If you have a distribution that's what's referred to as mound shaped, then usually you can get it to be approximately normal with fewer than 30. Okay. You have to have a really nasty distribution for it to be not approximately normal by the time it's 30. Usually 30 is good enough. Yes. We're going to use it. We're going to approximate it anyway. So we'll see what it is. We'll see how close it is with using 15. That's the idea. Okay. All right. So basically in all these problems then, we need to figure out the mean, we need to figure out the variance, and then we're just going to change it to a normal distribution and use that to approximate. That's the whole point of this. Okay? All right. This is why I said this is pretty cool, right? Basically, if your sample size is large enough, everything is normal. That's why we study the normal distribution so much. All right, so we need to figure out the mean and the variance of this distribution. How do we figure out the mean? What do we do? Say it again. Yeah, expected value of x, good. So we'll do integral from -1 to 1. of 3/2 x squared dx. Any guesses what the, 3/2 x, x times 3/2 x squared. That would be the expected value of this. Without doing any work, any guesses on what this answer is going to be? Yeah, it's going to be 0, isn't it? How do I know it's 0? X squared is symmetric about the y-axis, right? So it's going to split the area right in half at 0. So the mean is going to be 0. From a calculus perspective, I'm now integrating an odd function over an interval symmetric about the x-axis. I get 0. Right? So in any case, you're going to get 0. Variance. The first thing we need to compute is what? Expected value of x squared, right? So this will be 3/2 x to the 4th. Antiderivative will give you 3/10 x to the 5th. And so you'll get 3/5 when you're done. Assuming I did my calculus right. What's the variance then? It's also 3/5, isn't it? Because when we subtract off the mean squared, the mean was 0. Okay. All right, so now, what's the mean for y? Still 0. The variance for y is 15 times the 3/5. Good. So I just get 15? No, we don't. We get 9. Try that again. 15 divided by 5 is 3, not 5. Sorry. Yeah? Okay. So now we want the probability that y is between negative 0.3 and 1.5. Well, we now turn this into a normal distribution question. How are we going to attack it? Yep, switch it to z's, right? What do we need to do to switch it to z's? Yeah, well, I'll have to subtract 0, right? Because we subtract the mean. I'll just write it out that way. And divide by, by 3, square root of the variance, right? Oops. 1.5 minus 0 over square root of 9. Good. So 1.5 divided by 3 is 0.5. Negative 0.3 divided by 3 is negative 0.1. And without flipping over to a normal distribution table, let me just go grab it. Maybe, if I can find my normal distribution table. Where is it? Pi squared. Oh, that's t. My pages must be stuck together. There we go. 0.5 is 0.6915, and 0.1, that's negative 0.1. So I'm going to need to subtract 1 minus 0.5398. Yep. 0.4602, so we get 0.2313. Did my arithmetic right? Which is relatively close. But like Kevin said earlier, we only had a sample size of 15, right? So the n wasn't large enough yet to make it truly look like a normal. Okay? And what's the reason? I told you that if your distribution is mound shaped, right, looks like a mound, then it'll get to normal quicker, right? Well, our distribution certainly was not mound shaped. Our distribution looked like this, right? Kind of like the reverse of mound shaped, right? Okay. So, but it's still not bad. It's pretty close, right? If we took a higher random sample, it'd be even better. But this is how you use the central limit theorem on these problems. Questions on that one? We're going to do more. All right. Do the next one. Pardon me. This one we'll see if how we're pretty good, because we can talk about what the distribution actually is, and then we can use technology to help us out. Calculate the approximate value that the sum of the x's is greater than 57. So if I use y to be the sum of the x's, then what's the mean?
100 times
Good. Because they tell you the mean of each of the distributions is a half. That had nothing to do with it being exponential, right? The next part does. What's the variance of your y? Not squared. It's just we're just adding that because they're each individual ones now. Yeah, so we're just adding 100. So it's just 100 times 1/4. Yeah, we square the theta, right? We square the mean. Okay. So the mean's a half. The variance is a quarter. So we get 25. Remember, for exponential, the mean is theta. The variance is theta squared, right? Okay. So far, so good? So this is asking for the probability that y is greater than 57. What do we need to do? Complement it, good. And then change it to a z. So we'll subtract 57 minus what? 50 divided by 5. Good. Subtract the mean, divide by your standard deviation, right? We agree? 7/5 is what? 1.4? From the table, phi of 1.4 is 0.9192, so we get 0.0818. Nope, 0808, sorry. Arithmetic error. That okay? Yeah. Yeah, that's the mean for every single one of them, yeah. Because you're taking a random sample from the same distribution over and over again. So every single one of those, x1 to x100, would be the same distribution. Yep. All right. Let's see how close we got. If you do a sum of independent exponentials, what kind of distribution do you get? Gamma, right? Theta stays the same. The alpha goes up by how many things are in there, right? So your gamma or your theta was a half, and your alpha should be 100, right? All right. So we're gonna do 1 minus gamma. Probably can't see it. I got the wrong gamma. distribution. Oh, let me escape so I can actually zoom in. Sorry. I forget I have to do that before I start typing. Gamma distribution. 57 was the input, right? We just said that the alpha was 100. The beta is the theta in Excel, so 0.5. And we want cumulative. Fairly close. So this one we can check. Yes. The syntax? I can just open it back up here. This is what we can actually check, right, with technology to give us a little bit how good of an approximation we have. That one's much better than, as far as approximation goes, we were pretty close, much closer with this one than the previous one, right? All right. So let's do the next one. Don't save. All right, let's see what we got. 80 students take an actuarial science exam. Probability of passing is 0.55. And assuming students aren't cheating, we're going to assume that it's independent. Okay. All right. Calculate the probability that more than 50 pass. What type of distribution are we talking about here? You've got probability is the same for every single student passing. You've got 80 students. It's binomial, right? So this is a binomial distribution. We're going to approximate this with central limit theorem, okay? And basically, how are we thinking about the binomial? We just talked about this in a previous section. Sum of Bernoulli's is binomial, right? So we can think of these 80 students each as a Bernoulli random variable. 1 if they pass, 0 if they don't. And add it up. And that's going to give us our binomial, right? Okay. So in this case, our mean will be what? And this is binomial. Our mean will be, how do you calculate mean for a binomial? NP, right? 44. Should be able to multiply that one. It's just 40 plus 4. Okay. All right. Variance. Yeah, it's NPQ, right? So 80 times 0.55 times 0.45. And oh, goodness, if I remember what either of those squared was off the top of my head. I don't remember what either of those squared is off the top of my head. That's what a calculator's for, right? That's what a phone's for anymore, right? Get a calculator. I do love the jokes I see on the internet of, growing up, we were always told we wouldn't have a calculator with us all the time. Okay, 19.8. I mean, I didn't start regularly using a calculator until I was a junior in high school, if that tells you anything. I'm sure what it tells you, except that I'm old. But I mean, Dr. Dvorak used to use clay tablets, so I always get used to a hard time about being old. But he remembers using a slide rule. Have you seen slide rules before? We got a big one on the math suite. All right, anyway. Mean variance, okay? So we want probability of more than 50, right? So I'll just call it X. Again, we're going to use central limit theorem to approximate here, right? So the first thing we'll do is do the complement. So we'll do X is less than or equal to 50. In this case, we're going to check our answers with technology. I really do that equals is important in this case, right? Because binomial is discrete. So don't forget that piece, right? We've been doing continuous a while now. Don't forget on the exit final, if you've got a discrete one and you want to do a complement, don't forget to actually complement it, right? We've ignored the endpoints for so long. Okay. All right. We'll do 50 minus 44 over square root of 19.8. 6 divided by 19.8 square root. About 1.35. Roughly. No, this is where some rounding is definitely going to come up. 1.35. 9115. And so we'll get 0.0885 when we're done. Process okay on this one? The process is not any different than any other normal distribution that we've done, is it? It's just kind of nice, right? It's not really new. The only new concept is that we're using the fact that as we get higher and higher sample sizes, we can approximate it with normal distributions better and better. So this binomial that would have been a pain to compute by hand, because I would have to do 51 or 52 or 53 or 54 all the way up to or 80, right? That's greater than 50, isn't it? Okay. That would be a pain to do by hand unless you're using technology, and it's not so bad, which is what I'm going to do right this second. I should have just left Excel open. All right, so we'll do, where's my pen? So I can hit that. Okay, we'll do 1 minus binomial distribution. We want what less than or equal to 50, right? That was our upper cap. That was the equal. That's why I said it was important to keep track of that in this case. There were 80 trials. The probability of success was 0.55, and this one is cumulative. 0.07. This is worse than I would have thought. This one should have come out to be pretty good. Didn't make any errors with arithmetic, did it? Just making sure I didn't make any arithmetic error along the way, because that should have come out better than it did. Now, it could just be the rounding error for the 1.35 versus, oh, that is what it is. 1.34 is 0.099 or 9099, and 0.135 is 0.19115. We got some pretty bigger, a little bit bigger rounding error. So that's probably what's causing part of the problem. But anyway, the process okay. My approximation didn't show up very nicely. Well, it also is the case that 0.55 is a pretty decent sized probability, so we're probably not as mound shaped as we would have liked for our distribution. Might be part of the problem. There's also the issue of approximating a discrete distribution with a continuous one. Because if I think about, let me just draw up on the board here. If you think about, say, a frequency histogram looking something like this, you're trying to approximate it with something going through like that, right? So at any particular point, you're kind of missing and gaining. So it'd be better to use a midpoint idea here with the normal distribution than using what we used, which is at the endpoint itself, right? So I probably should have used 50.5. That's what they call continuity correction. Go right in the middle. Use 50.5 rather than 50. to try to eliminate the fact that I want to catch 50 on the way down rather than just touching 50 and going on. Okay, you see what I mean by I'm missing some and gaining some here? So if I went to the left a little bit, I would be gaining what I don't want. So let me do 50.5 minus 44 and then divide by 19.8. And maybe I'll get a little bit better here. Oh, yeah, that made it much better. 1.46 was the z-score in that case. And if I do 1 minus 0.9279, I would have got 0.0721 versus 0.0712. I got a much better approximation. Okay, that's a different. That's a concept for a different day. Okay, but that's what's referred to as continuity correction. We're trying to approximate a discrete distribution using a continuous one. And so if I think about you've done things like this in calculus, right? When you've done approximations with integration, right? Using a midpoint in this case would be a much better approximation for the integral than using a left or a right endpoint. And doing it the way we did it, we used an endpoint, right? In particular, the endpoint we used would have included 50 in the answer, which gave us the extra piece of information we didn't want, which made the probability go up. We wanted to eliminate 50. So starting at 50 and a half would have been a better approximation to eliminate some of that probability. Like I said, that's a different discussion for a different day. Okay, this is just a use the central limit theorem idea. And this is literally the central limit theorem idea that we just did here. So is this process okay? All right, let's see if we can attack one with a mean. That was just approximating a chi-square, doing the same thing. It's the same type of idea. I'm going to skip that one. Let's see if we can do one with a mean. Because remember, again, the mean changes some things. I mean, it's going to keep it normal, but it's going to change some things. Part A just asks you for the mean of the distribution, right? So we want the mean of this distribution here. All right, so mean and variance. So we'll do the integral from 0 to 2 of x times 1 minus x over 2 dx. And the variance of, we'll need expected value of x to start with. Expected value of x squared to start with. So we'll do x minus x squared over 2. 1/2 x squared minus x cubed over 6. And I think you get 2/3. Just as a little side note here, if you've done any physics, and done anything with centers of mass, this is a right triangle, so I can figure out how far to the right I need to go to balance that area. And since it's a triangle, it goes 1/3 of the way over. So I could have just looked at the picture and got the fact that the mean should be 2/3. That corresponds to physics. I know some of you have physics, so I was trying to relate that to other topics. You can ignore me if you want to. I mean, you always have that option, right? You can always ignore me. It's fine. I try to make connections to other things and why we care about these things. All right, so distribute your x squared through in the next case. We'll be integrating x squared minus x cubed over 2. Antiderivative of x squared is x cubed over 3. For x cubed, we'll get x to the 4th over 8. Put in 0, we obviously get 0. At least I hope it's obvious we get 0. Put in 2, we get 8 thirds minus a 2. Yeah, so I get 2 thirds again. Assuming I did my arithmetic right. But now for variance, we'll need to subtract off the mean squared. We'll get 2 thirds minus 4 ninths, so we should get 2 ninths when we're done. Yeah? Okay. All right, so that's what part A was. A little bit of a review for finding mean and variance, but the important part is approximate this probability. Okay? So again, if we have a random sample taken from a normal distribution with mean mu and variance sigma squared, then what's the distribution of x bar? Normal, mean, mu, variance over n. Good. Okay. So we're going to use this same exact concept using central limit theorem for means of distributions, just like we did for sums. Okay? Because all we're doing for a mean is multiplying the all you do for the mean is multiply the sum by a constant, right? You do the sum multiplied by 1 over n, right? So it's the same exact concept that you're doing for a central limit theorem. We just have to make sure that we adjust our variance correctly. So now we want, pardon me, we want probability that 2 thirds is less than or equal to x bar is less than or equal to 5/6. We will do, we'll split it like we always do, right? This is nothing new, right? That's not new. The new part comes in with making a z-score, right? In each case, what are we going to subtract off? 2 thirds. So we'll have 5/6 minus 2 thirds. 2 thirds minus 2 thirds. And in each case, what will we divide by?
Square root of 2 ninths over 18.
Good. You got to take your square root, right? Don't forget to take the square root of your variance, right? So we'll do the square root of 2 ninths over 18. 2 ninths over 18 is just 1 over 81. Square root of that will give you a ninth, right? The second one is just 0, since I got a 0 on top. Oh, so I'm going to multiply. Well, 5/6 minus 2 thirds is a sixth times 9 is 1.5. I think Trace is checking me. Phi of 1.5 is 0.9332. Shouldn't have to look up phi of 0. What is phi of 0 equal to? 0.5. Hey, good. You're all over it. Awesome. So there's our approximate probability. Is okay? All right. Let's do one more.
I want to do this one or the next one. Let me look. Ooh, let's do the next one. This one again asks us to use a normal approximation to calculate the probability of 80 or more. You've got 500 insurance policies. Claims follow a Poisson distribution with a mean of 0.2. It says the number of claims. Claim counts are independent, and you want 80 or more claims. So notice in this one, you are adding together 500 Poisson distributions, right? The one's total number of claims being more than 80. But what do we know about sums of Poisson? That's a Poisson, good. Sum of Poissons is Poisson. What do you do with the lambdas? Yeah, just n lambda, right? So the Poisson here, so this one is your lambda originally was 0.2. We'll take the 0.2 times 500, gives you 100, right? What's the variance? So that's your mean, right? The lambda is the mean. What's the variance? The same, yeah. It's 100, right? Notice in this case it's a sum of Poisson, right? We're aggregating claims. We're not doing a mean number of claims, right? Okay. So we want the probability of x is greater than or equal to 80, right? Agree with that? Now, thinking about it from a discrete standpoint, since this is Poisson, if I do the complement, I would want 1 minus the probability that x is less than or equal to 79, right? We agree? Okay. Here's where your central limit theorem comes in. I would take my 79, what would we subtract? 100, and divide by the square root of 100, divide by 10. Right? So we should get negative 2.1. If I did that right. 21 divided by 10. Negative 21 divided by 10. Yeah. So that should just be phi of 2.1, which is 0.9821. Now, since this is a discrete distribution, if I were thinking about that continuity correction again, I want to subtract off the x equaling 79 and keep the 80, right? The 80's in the good spot, the 79's in the bad spot we're trying to subtract off. So if I were using that continuity correction idea to make our approximation a little bit better, I would have put in a 0.5 here and said 79.5 to make sure that we were subtracting off the 79. Okay. And it would make it a little bit better. I'm not going to worry about that for the exam at all. I'm just mentioning that you want to make it a little bit better with approximating discrete distributions with continuous ones. There's this continuity correction idea. Okay. That okay? We feel pretty good about that? That's not too bad? I mean, it's normal distribution problems again, right? Just make sure you have the right mean and the variance. Okay. So, final exam stuff. Did everybody get one of the extra sheets that I gave out with the topics? Okay. So, pardon me. Goodness. The beginning stuff is just definitions of stuff that we've done over and over again during the course of the semester, but just to remind, making sure that when you do probabilities of unions, make sure that you subtract off the intersection piece, right? If there is anything, unless they're mutually exclusive. Probabilities of intersections, you multiply, right? You have to pay attention to whether or not the events are independent when you do the multiplication, right? Those kind of things. So basically, those kind of 4 ideas at the top are kind of all linked together, right? To do unions, I got to do intersections. To do intersections, I need to have the concept of are they independent or not? If they're not independent, then there must be some conditional probability piece playing in there, right? So they're all kind of interconnected there, those first 4. Expected values, being able to compute those things. We talked about those. And we've certainly done enough with CDFs and PDFs, how to calculate those. We've done, the last exam, in fact, had what joint PDFs were, what marginal PDFs were, and what conditional PDFs were, right? Now to find those, that was just the last exam. Making sure that you know your special distributions again, and those PDFs and means and variances, because those are going to pop up, right? Notice that the PDFs themselves didn't pop up, but knowing what the mean and variance of a Poisson just popped up in the example problem we just did. Knowing what the mean and variance of an exponential function just popped up in the previous example, right? So making sure that you know all of those things is important to be able to do other types of problems. And then, of course, we just talked about central limit theorem, so what it states. Like I said, basically, central limit theorem means everything's normal eventually. Right? Make your sample size big enough, everything's normal. Okay. All right. How to calculate covariance and how to calculate correlation. That stuff was on the last exam. Apparently, I didn't get the error key after one of this. Making sure that you know how to calculate your probabilities with iterated integrals. That was just on the last exam as well. And then that's just kind of the definition type of thing. That was the first part. Then what are the calculation types of things that you need to do? Just kind of a reminder of things maybe that were older things. Bayes' theorem. Don't forget about Bayes' theorem. That comes up a lot. Many of you have seen Bayes' theorem in other classes, right? I think it's been in intro to data science. It's been in artificial intelligence. It's been in lots of different classes, right? So probably going to show up on the final. I would hazard a guess it'll be on there. Making sure you can do the problems like we just talked about today. And they're not bad, right? They're just normal distribution problems. Okay. Making sure you can use your normal distribution table. More important than being able to use the chi-square distribution table. We're focusing more on probabilities with normal distributions, right? I have the chi-squared on there, but worry about the normal distribution table itself. That's more important. Okay. As far as finding PDFs and CDFs, those order statistics, remember that's really just max and min, and that was just on the last test. We did a maximum one, right, on the last test here. And then transformations, we only did single variable transformations besides the max and mins. We only did single variable transformations. And there was one like that on the exam as well that you just took. Being able to find various calculation types of things, right? Mean, variance, standard deviation, covariance, correlation, those kind of things. Knowing what moment generating functions are and how to find them. In particular, making sure you can find the moment generating function of a sum. That's later on. That's another bullet point later on. And then the different connections between distributions. We had connections that we talked about earlier in the semester, and then extended that list just recently, right? And then if you prefer to use formulas for the transformations that versus just doing them directly from the CDF doing them directly from the CDF, I gave you the formulas for if you've got a single variable transformation, how to find the PDF, and if you've got a max or a min, how to find that. Those are the formulas for those. So you don't have to recreate them if you don't want to. All right. I will go through your old exams and point out problems on the old exams to go focus on. And then you can find the corresponding ones that would be on review sheets as well. That would make sense to look at. And I will post that on Moodle. As a matter of fact, what I'll do is I'll take blank copies of the old exams in case you want to work through them again. And I'll post those, and in the header for the file, or for the link, I mean, I'll put which problems to look at on those. Okay. Say it again. For the counting, you might have to do a little bit of counting, but probably not anything really difficult. I mean, you'll have to know what a combination binomial coefficient is, but nothing horribly complicated for counting problems. No. That's not the point. I have a whole other class that you can do for lots of counting things. You might have to do simple counting things, but nothing horrible. Any questions at all? I'll be around tomorrow, and I'll be around on Monday. I give a final from 10 to 12 on Monday, but otherwise, and I have a meeting at 3:30, but I'll be around otherwise on Monday. If you've got questions, then I'll be in before our final as well on Tuesday. Okay. Of course, always feel free to email me if you need to. Happy to do that. All right. Was that a you one, Rose? I'm sorry. Wasn't trying to leave you out. Yeah.
What did you think about the pizza stuff?
Yeah, what I'm gonna do is I'll put it in there if you need it for a
Okay.
borderline.
Do you know how much it'll be, or just if it's like really close?
If it's really close. Yeah. We'll just bump it.
Okay.
Yep.
Thank you.
You're welcome.